Hi, everyone. Good evening to all of you. We maybe many people are participating from different parts of the world, so we may have different time zones between all of us. But yeah, we are based in India. I would say good evening to all of you. Thanks a lot for everyone joining today in the webinar. Uh, it's a quick catch up. Uh, with specific topics that we dive into an exposure that we have built over the number of days, months, and years that we have been working on the projects. Specifically, BMS is a very interesting project at Decibels Lab. We've been working on that for about 4+ years now. Um, the journey which started just as an interest to work on the BMS, but today we are developing our own BMS, also the complete algorithms, and we are providing those products to applications such as energy storage. So it's a good, interesting thing that we talk about it, uh, on how we have been doing them. Also, there are courses at Decibels Lab which teaches exclusively on developing BMS algorithms and implementing BMS algorithms in the real-time hardware. Uh, Today's webinar topic is on the challenges in SOC estimation. Uh, it's fairly common topic that we always come across, that what is this challenges are, and why does this challenge exists, and then how do we overcome these challenges when we're developing the software, and how do we identify them uh, as issues, and is there any solution that we can provide, or this is just the way it could be, um, without getting fixed, right? Um, so that's the context of today's webinar, which we will talk length and breadth of it. If you have questions during the webinar, feel free to drop them in the chat box. Um, Maybe at certain phases of the webinar, I will take questions. Um, that would be appropriate, or else the whole webinar will become a discussion, right? Um, cool. So even to set a context, and also get the weightage of today's uh, webinar, I would be glad if any one of you can just drop a message of what are you interested to learn today, so that possibly I will be able to expand the context of a webinar. I have some topics that I can talk about today, but if somebody is able to have any specific questions or any expectations, I would be lovely to take those questions and expectations and maybe take them as an input to today's webinar. Okay, so talk about difficulties in estimation. Perfect. That's absolutely we're going to talk. I'm a project engineer working on battery level R&D, wants to bridge my skills with model level expertise. Interesting. I hope my audio is good, Vinayak. Is it audible well for you?
Yes, it's audible.
Okay, super. Great. So if anybody would like to drop a text, let's just take 1 minute, and we can go to the topics that we predefined if there is no specific expectations. Yep. There are some of the topics that we have picked up to talk today. If anybody having um, specific interest, you can put those questions in the chat box. I'll try to take them if we can address them in today's webinar, or we will do a rollover to the upcoming webinars. Okay, I see one. Please do a little introduction to, I have no prior knowledge on it. Okay. Aging capacity fade. All right. Anybody else would like to drop in messages? All right. So if just one topic that came in, what is SOC? I think this is sort of a prerequisite to this session, right? Because we're talking about challenges in SOC estimation, but what is SOC? It is the amount of charge that is available at a given time in a cell or a pack. It is just like a water tank or a water bottle. How much water is left inside the tank? Is it full? Is it half full? Or what is the amount of water that we have? The same way in battery, right? When you have your phone, you see when you charge your phone, the battery SOC start increasing. When you use your phone, the batteries start to degrade, correct? Uh, the same way when you use your phone for many number of years, the battery usage is limited by less number of hours because the battery would have got degraded over the number of usage cycles. So it is basically an information that indicates the amount of charge at any given time inside the cell, if it is at a single cell, or inside the pack, which is combination of cells. Okay, that's the state of charge. So it looks very simple because it is the information of charge that is available. But the problem is that we do not know, like a water, that we cannot see the charge that is present inside the cell. Uh, what is charge? It's basically the shuttling of ions, that is lithium ions from anode to cathode, cathode to anode, while you're doing a charging or a discharging process, right? When you manufacture an electrode, so you have lithium sitting on the cathode side and manufacture the cell. And then when you do your formation cycle, you charge the battery and then you discharge the battery, right? So when you charge the battery, the ions flow from cathode to an anode through an electrolyte in a typical uh, lithium-ion cell. If it is a solid-state battery, you may not have a liquid like an electrolyte, which would it will have a different medium to uh, pass the ions inside the cell. So when you discharge, the ions goes from an anode to a cathode, and this whole shuttling process happens. So this is basically what is charging and discharging of the battery. So fundamentally, you would like to know at a very, very basic level how many ions you may have at anode, you may have at cathode at any given time, right? Uh, because they are so small, they are so tiny, you don't get to see them, right? You don't get to measure them easily. Uh, because there are millions and millions of them as small components. So you don't really know what is the amount of charge practically measurable inside the cell, right? That's why we call it as estimation. We're trying to estimate, oh, this may be the amount of charge that is inside the cell because you're not physically seeing those ions which are present inside the cell. Uh, you're trying to assume certain parameters and trying to say, okay, hey, this is possibly the amount of charge that is present inside that. So that becomes a limitation that you're not measuring the state of charge, you are estimating the state of charge, okay? Assuming certain things. For example, let's take a bottle of a water, right? And then you can see if it is a transparent water bottle. You can pour out some amount of water. If you measure the amount of water that you poured, so you know what is left inside the bottle. Or if you still just have an option to measure it, so you can see that. Imagine if the temperature of the water is quite high. Okay. Imagine if the temperature of the hot water is quite high because then the density of the water changes, right? So Would I be able to correlate in the same way the amount of water? You can, but there would be a small error that get added into it when you're trying to say, okay, this is the exact amount of water that is there because the density of the water has changed, correct? Now, the same thing inside the cell as well, basically, which impacts the amount of charge that is present in the cell is dependent upon a variety of features that influences the capacity of the cell, correct? So that is basically what is creating as a challenges that becomes a difficulty to actually estimate exact amount of charge that is present inside the cell. So to take that question, I'm not sure if I built you an idea, right? Uh, Fundamentally, we have an ion that is floating from a cathode to anode and anode to cathode. That is basically your charge, right? That is what it creates an option to let the electrons out and electrons in into the cell. So at any given time, you want to know the amount of possible charge that is available at the cell or at the pack. And but you cannot really measure the ions, and there are millions of them and billions of them inside the cell. So you possibly want to consider certain parameters and say, hey, this is the possible available charge at any given time. And that's basically a state of charge. Uh, Interesting. So there are people who have put across questions, so we take one by one, and try to see through how much we can address. Okay. So let's go the first thing about the variability of the cell. Okay. When when you have a pack, the pack is combination of cells, right? So it is not a single cell. At least it is easier, slightly easier to do it at a cell level. If you take applications like earphones, your mobiles, they usually have a one cell, okay? And that cells will power up the mobile phone, or it will power up the earphones and things like that. But it is slightly easy to do an SOC estimation if it is a single cell, okay? But if there are multiple cells, they would not be having the exact, you know, perfection of chemistry what another cell has. There would be a slight variation. When during the manufacturing, let's say you manufacture 1,000 cells, among 1,000 cells, not all 1,000 cells have been formed in the same way, have been having a formation cycle in the same way, having a same formation of SEI during the formation cycle, or anything, during its operation have some variations, right? So which is typically we have the few cells in the pack, and then when you're trying to measure the voltage across these few cells, not all of them are same, right? So maybe if one cell is at 4 volts, maybe another cell is at maybe 3.995 volts, and it is having a difference of 0.05 volts. Um, then maybe there is another cell which is at 4.05 volts, right? So all the cells which are in the pack may have slightly different voltages, though you would have put them like uh, charging them to a specific voltage and then trying to put inside the battery. But because of small variations inside them, they may have slight differences. Now, how would I say if these cells have different voltages, that means they may have at different capacity levels, then how do I combine all of those variations in place? And then I would say, hey, this is the SOC of the battery. Example like this, let's say you have 10 water bottles and there is a small difference of a water levels in each of those water bottles. And then combined, you want to say, hey, what is the amount of water that you can get uh, by removing the water from each of these bottles, right? Which may be fairly easy to do that. uh, because you can measure it. But here, you don't get to measure it directly, right? So, and it is integrated as a complete pack. So you would, if there's a small variations in the cell voltages, and that means you don't have exact amount of capacity in all the cells, then how would you say that the output, what I'm trying to measure as an SOC, is not same for all the cells. Maybe one cell is at 95.5, another cell is at 95.4, maybe another cell is at 95.3, right? So this is basically what creates a slight difficulty because not all the cells are at the same voltage. Okay. Because of maybe internal resistance, because of they would have kept at a different place inside the battery. Maybe one cell would have exposed to higher temperature. Maybe other cells would have got cooled down a bit early and have a better exposure to thermal heat dissipation, right? And then these situations, which is basically can say at a pack level, we just don't have one cell, right? So we have multiple cells. And then we are trying to measure the SOC for all those cells together as a one value. And then there is variations inside these individual cells would create sort of a measurement difference of your SOC. So what is the solution? Um, you can set a threshold, all right, to a manufacturer because BMS is not something like a god which can fix any problems in the world and do every type of measurement and estimations. So it can only do a correct estimation if the pack is good. Okay. If the pack has a variety of cells which are having different internal resistance, different batch of production, right? And different rate of degradation across them, maybe incorrect distribution of temperature. All of them would create certain variations of measurements across the cell, across the pack. And that variation, which is inbuilt already in the pack, would contribute into uh, inaccuracies of estimating then SOC estimation. So what is the solution? So ask the pack manufacturer to ensure, let's say when you discharge the battery, you can measure the voltage across each cell terminal. I would say each series terminal, right? And check between any two cells, what is the maximum delta you can have, okay? If the value is more than certain threshold, then there is nothing that BMS can do. And it is basically an inherent problem of the battery that could be incorrect sorting of the cells, incorrect quality of the cells, or incorrect electrical design, maybe the bus bar length, the arrangement of cells in series parallel configurations, right? All of this would inherently contribute into a variation in the, the, the voltages across each cells, right? Or incorrect degradation, incorrect thermal management of the batteries. So that this is something creates a measurement error, not a measurement error, differences in voltages. And then that difference cannot be averaged. So when you say you average all of this and say this is an average SOC, then you would have some other problems that we will discuss in the upcoming slides. So what is the solution? Tell the manufacturer if there is an X difference in voltage during charging and discharging cycle, fix your battery first, then the BMS would try to do its best job in estimating an SOC. Any questions we can take? Any questions on the specific topic, variability of cells? Okay, so if you have a pack that is having certain variations like this, uh, you can ask the manufacturer to see if there is not an issue with the BMS. So what you can do when you log the data of the BMS, you would see a curves like this, maybe, right? So this is not an exact curve because it's in rest and this is in discharge. But imagine there are two cells, right, which are getting charged or discharged. Imagine if there is a difference between the two cells like this, which is showed in the slides right now. That is sort of a representation that there is something wrong. So you can have a threshold. How much of the threshold, it typically depends upon you to decide. But yeah, there shouldn't be any threshold that would be there like that. Okay. Uh, what are the possible voltage differences you're talking about? What are the possible voltage differences? Why? Uh, what are the possible voltage differences is possibly when we spoke about some of these points, right? Imagine the cells which you have put in the parallel line um, would have certain variations in its capacity because it is not same, right? When the capacity of, let's say you take 10 cells and you put them in parallel. Among 10 cells, maybe two cells are slightly having uh, uh, a degradation and other eight cells are bad. Other eight cells are good. So the capacity is slightly different inside these cells, right? Which is basically the way the voltage also operates. If you draw the current, the voltage would possibly drip in those two cells slightly more than compared to those eight cells. Then if you measure the overall voltage across your parallel, then you would have a slightly less voltage because those two cells are slightly dipped faster. So that's kind of a voltage difference we can talk about. If you have a temperature difference, for example, like some cells in the middle are hotter, the cells near the edges of the battery pack are slightly colder because they can dissipate the heat faster to the environment through the metal casings and things like that. So because of these, there are cells which are maybe degraded faster, and the cells which are having a better temperature maintenance would have a better health. So all of these things would create an imbalance across the pack. Okay. This orange voltage line seems to drop near lower voltage uh, if one cell is among them is low voltage. Okay, that is just a representation. Uh, Please throw some light on different check on manufacturer side to check the cells and arranging a pack. All right, so the biggest difficulty at any manufacturer is that how much time we could spare, right? So we want to make a pack as early as possible. That means there is very less amount of time to manufacture a pack. Any manufacturer would do two type of tests. One is the open circuit voltage test and the IR test. IR, it is typically an AC IR with the measure because it is easy to measure. We don't need to do any load on the cell or discharge or charge the current from the cell. So, which is an AC approach of measuring a specific AC internal resistance. So, those are the only two tests I have seen any manufacturer would do. They wouldn't do more than that. They intended to make sure that the supplier of the cells will supply them the the good cells, okay, and expect to have least amount of variability. There is a possibility you can do a capacity test, but you cannot have you cannot have time to afford to test the full charging and discharging of the cell because you would waste a lot of time and money, and you cannot manufacture a lot of packs. So anyone, as I come across, would only measure two parameters, which is OCV of the cell and internal resistance of the cell, and then they sort the cells based on that. Um, it is possibly an arrangement that and a confidence that you have with your supplier to ensure to have a best possible quality output. Uh, from the cells that they have manufactured. And the rest is an electrical design and a thermal design of the battery pack. Okay, so we are observing cell unbalancing in new battery pack. Could you please clarify whether it is typically originates from the um, cell inside, like a cell capacity or impedance variation, or from the BMS side, unlike sensing and balancing circuit issues? We are observing cell balancing in the new battery packs. All right. So inherently as a nature, right? So the imbalances are because of intrinsic nature of the cell. That could be one important thing, right? Or the second thing is possibly uh, because of the way how electrically the battery pack has been assembled. When you draw the current, do you equally draw the current from each cell, right? Or you don't, your electrical design is not in a right way that it may only draw more current from the cells which are very closest to the terminal, right? Is your internal resistance commonly distributed across the pack? Is the thermal distribution is commonly across the pack? Are the typical reasons why you would see an imbalance? It is considered that the BMS should not draw a lot of current from individual cells and things like that, that you would see a variation because of the BMS. BMS do draw a small amount of current to keep itself alive because there is DC-DC converter, a buck converter, which takes the 48 volt or 24 volts and converts to 5 volts to keep the BMS running. Uh, it's I assume it's possibly the intrinsic nature of the pack that is creating the imbalance. We do DCIR HPPC. DCIR HPPC are something similar. Uh, the thing is that we don't have that much of time, possibly, if I assume that you need to load the cell and then do a one cycle of charge and discharge, or only a discharge. Then you can see the drop in voltage to measure an internal resistance, like a DC internal resistance. But this process consumes time and also the current that you have to subject the cell to. So in the manufacturing process of making thousands of packs, it becomes a limitation to do a DCAR at many places. That's why people have ACIR or open circuit voltage measurement. So how exactly cells are arranged in a pack when it comes to a good and bad cells and good or cells, good or with good cell, good voltage levels, or vice versa? Um, I would say you you don't need to put any bad cells in the pack. That should be an ideal condition. If there is any voltage differences between the cells that you're trying to assemble, I would say don't assemble them into the pack would be a ideal thing to do because do a lot of other they will create a lot of other challenges when they operate over the number of cycles. Okay, there is an acceptable limit again according to your battery pack considerations and what you want to achieve. Maybe like 5 millivolts, 10 millivolts, 20 millivolts is something acceptable. All right, and because your BMS can do um, kind of a balancing, right? And that would possibly fulfill the situation that you may come across in the real world operations, right? But there is an acceptable limit. That is something up to the company to decide how much is an acceptable limit between the voltage variations. Okay, so the OCV SOC relationship is another topic which is interesting, right? Um, Maybe as I was giving you an example of a bottle of water. So you know when you see the water bottle that how much is the water in the bottle, you can clearly say, you can compare that as a voltage. Imagine 0 volt to 5 volt. If the bottle is full, it is like a 5 volts. If the bottle is half, it is 2.5 volt. If the bottle is having no water, it's kind of 0 volts, right? But in the cell, it is not like same and straightforward. If the cell is at zero, that means cell is dead. Okay. It is not that it is at 0% SOC. So we have an operability for the cell, like an under voltage limit and an upper voltage limit. Okay. So we do not take the cells to a 0 volt at all. An MC cell, LFP cell has its own operatable limit, which you see in the example of image here, which is kind of a characteristic for an LFP cell. Okay. So it has a lower limit of 2 volts and an upper limit of 3.6 volts. So when it is at 2 volts, maybe the SOC is 0. When it is at 3.6 volts, the SOC is 100%. Okay. This is something that we assume that is correct. And this is given by the manufacturer. Okay. So that means when you charge the battery, you charge it till an X voltage, and then you discharge the battery, I'm sorry, a cell, considered to be a pack as well if you take it. So you discharge it only till its specific defined voltage. So the cell always operates between this voltage. So there is a slightly a closer relationship that you can draw. Okay. Uh, when you're charging the battery, it is in terminal voltage. When you're discharging the battery, that means it is in terminal voltage, right? So the open circuit voltage is when there is no load on the cell for a specific duration of time. That means when you're discharging the cell, uh, you have an internal resistance contributing into a voltage measurement. Okay. When you leave the load, the cells slightly bounce back, the spring back, and slightly start to rest. Okay. And it springs back for some amount of time and then it becomes stabilized. Um, the state at which there is no load and uh, there is no relaxation voltage of the cell, that means the cell voltage is fully stabilized, and that would be an OCV stage of the cell. Okay. And we can draw some amount of relationship, I would say closest relationship with OCV of the cell. Okay. If you measure the voltage of the cell, open circuit voltage of the cell, you can form a table and then you can correlate your OCV and an SOC, which is one of the very fundamental way of measuring an SOC. Okay, an OCV based association estimation. The two problems with that, two challenges to do it in that way is that challenge number one, when you have a pack, correct, you don't just have one cell. You take measurement and say, hey, this is your SOC. Okay. In a pack, you have combination of cells, right? And let's say you have a battery pack for 14S. So you have 14 cell voltage measurements, correct? So how do you choose which cell I will consider to say this is the SOC of the pack, correct? If it is just your mobile phone, then you just have one cell, correct? It is very easy to just measure its voltage and then say, okay, hey, this is SOC. But when it is a pack, then you have more number of cells in series and you're measuring 14 cell voltages as an example. Which cell do you consider for identifying, hey, this is my pack voltage? Sorry, this is my pack's SOC, correct? So you can take the lowest cell voltage, then it may be incorrect. You can take a highest cell voltage, it may be incorrect as well. You can take an average voltage, a mean voltage, something which is more ideal, but the distribution of error will be slightly different, right? Or you can take the closest 6 voltages or 7 voltages across 14 cells and then say, okay, hey, this would be the right one. But ideally, you're not truly telling which voltage, right? Which SOC. So you're taking in some combination of X and Y and Z and defining this maybe an right SOC, correct? This would have its own challenges because you're not truly telling which cell's SOC is your PAC's SOC, correct? Excuse me for a second. So that's one of the problem when you say with a pack. So what is the solution? Don't have imbalances in your pack. If there is imbalance in your pack, certainly and certainly there will be errors that accumulates across when you do OCV based resetting or correcting the algorithms back to referring to an OCV for calibrations. So if the pack is imbalanced above a specific limit, anything that you're trying to do, and when the pack's under the load conditions would have a lot of variation when you measure an SOC, or one of the cell which is having slightly imbalance would hit an under voltage, and then your BMS will cut off, and maybe the SOC would get clamped to 0 or 100%. So there would be some sudden jump of SOC from, let's say, 5% to 0% or 95% to 100%. So just as an input that OCV is good. It's very straightforward. If you have a OCV graph, you can tell, hey, I measure an voltage, I tell the SOC of the cell or a pack. But if you have a pack, there are many cells. Which cell do you consider as right voltage to say an SOC? And the second thing is that the voltage curve of an LFP is highly flat in nature, like in these regions, right? At some ranges like 40% to 60% or 30% to 70%, you don't see much voltage drop that is happening, right? And if you don't have very precise voltage measurement, you may not have an accurate information of the voltage. So you may be incorrectly updating state of charge of the BMS, state of charge in the BMS. So a quick and NMC is slightly better, slightly okay, wouldn't be an issue. But if the LFP, because of its certain intrinsic characteristics of the voltage, you may get into some troubles of right SOC estimation. And that's just a quick input about the OCV based OCV SOC relationship, and then um, what are the limitations that we may face with respect to these um measuring in SOC with a OCV approach. Um, okay, so how does this plateau region, mostly flat, can be estimated? Interesting, yeah. That's a typical problem with LFP cells, right? So that is why estimating an SOC for an LFP is slightly much challenging than in an MC. That is when common algorithms like Coulomb counting or an open circuit voltage based SOC estimation or combining both of them would fail. And that is when we intended to move towards like a Kalman filter based SOC estimation, where we have theoretical cell and a real measurement, and we do kind of all the mathematical formulations to adjust the error and which is between your real measurement and theoretical measurement, and try to correlate as closest as possible to a try to estimate as closest as possible to a realistic voltage. So certainly it is a challenge, and that is why just an OCV based SOC is not sufficient. You go for something slightly more advanced with the help of Kalman filter based algorithms, um, which is practically implementable in the BMS. So, okay, so I am working in one of our BESS sites where multiple inverters share the same AC bus. One inverter is showing a fault. Its AC side filter sees too much current from DAS. I have noticed that inverter voltage aren't always perfectly in sync. Could this be related to a battery SOC or pack imbalances? Do you have any suggestions on how we could prevent the voltage differences from causing failures? Um, I may not just write to comment. This would be the answer. But if you have a data, check the the voltages across the packs. Um, and try to see if the voltage of the packs, wherever this multiple inverters are connected, having and same DC output from the pack, verify if 10 packs are there, of the 10 packs are at the same voltage. Certainly you have your inverter has a job to take care of, even though the cell volt pack voltage is 1 volt difference between each other, or next pack, the inverter possibly has its ability to step it up and then bring out the voltage. Maybe it'll deliver a less current, but it tend to manage its voltage at a same level. But check if that is the situation, and maybe based on that, I would be able to give you more answers. Please explain hysteresis behavior in LFP. Okay. Comparison can help me in SOC estimation in LFP. Um, okay. So KF, AKF, and particle filter. At a broad level, each of them have its advantages. Okay. EKF being slightly simpler than UKF and then particle filter, and easier for computational load of your microcontroller to approach. And it could be UKF would be the more ideal on certain situations, but based on all of these algorithms are based on what the parameters that you're trying to feed into them. Maybe do you have such amount of data that is available for you to feed? Is those data is correct? If you haven't tried anything, start with EKF. It would be very ideal. Then move to UKF. So you would clearly see a learning journey that you could have uh, through this process than directly jumping into UKF and then getting stuck at the point and don't know what is my improvisation based on EKF. The particle filters are slightly challenging to get implemented on the hardware depending upon which microcontrollers you're trying to use. It requires slightly and higher computational power. So start with EKF, then move to UniKF and see through if you're able to really, really optimize your parameters that you're able to feed into the model. Okay, so people have approached it that they try to do EKF in the mid region and then they switch back to the normal algorithms um, on both the sides, lower and a higher side. It depends how do you want to approach it. I see and I've heard people get better results for doing that. I don't today have a data that I can share it to you. Okay. So, and then the next topic is the current sensor noise. Okay. Um, this is sort of a realistic data that we are getting from the current sensor. The sensor that you're having in your BMS would also have its noise, right? So it may not be truly measuring the current that is flowing through the sensor, right? And it is having its own limitations to measure. We have shunt type and we have Hall type, all right? Uh, kind of a current transformers also. All of them have their own limitations on amount of current that they can measure. Let's say the BMS has 1 amp current that is going through it. The current sensor have its own ability to measure. Let's say you're doing a bus or an energy storage applications like the BESS, right? Where you have in a megawatt scale. So maybe the current sensor is not very sensitive to measure 1 amp or a 2 amp level current, correct? So maybe at times the 1 amp is flowing through the battery, out of the battery, but current sensor is not able to pick it up. So you don't really know whether you're actually discharging or not. Okay. That is in terms of how much current the sensor can measure, right? The second point is that when it is measuring, it is how truly that data is correct, which you measure, which you're reading, correct? Because if you're having a shunt, then you are measuring the voltage drop. Then you're trying to take that voltage drop, do all the amplification, and then send that to an ADC, and then convert that into a value, and then take it as a current. Correct. If it is any other type of sensor, like a current transformer, you're trying to have a primary coil and the secondary coil kind of a thing. So try to produce a voltage in them. So you're trying to have a measurement of the current by certain indirect ways. So it'll have its own noises inbuilt in them. And if you're measuring 1 amp, no, it won't be dead 1 amp. It would be having like jittering around it. If you take it over, let's say 24 hours, the small variations, if you take them over 24 hours, you may have accounted some measurements. And that may not be true, but you have measured that, right? And that contributes also in uh, the estimate. It also accounted in Coulomb counting, and then that creates an issue. So a closest calibration of the current sensor, drifting of current sensor with respect to temperature, drifting of current sensor with respect to the age of the sensor, and also how accuracy of that sensor is true at any given time would be the parameters that you account when you try to do include some of your estimations with the help of sense that you try to have. We'll quickly take questions. Industrial sensors mostly use Hall effect sensors. Okay, it depends upon what is the amount of current that you want to measure. Mostly big applications, they will go for a Hall-based or a CT-based, based on uh, maybe a kilowatt scale, right? If you want to go for like a 50, 60 kilowatt, you would definitely go for a Hall-based or a current transformer. Any other questions anybody have? Um, just the other question is that these activity of Kalman filters or UKFs and things like that also helps you in reducing these noises. But you need to know certain parameters of the sensor to feed them into the filter. And that is not something quite common and easily available as a data that will put you through some of the efforts to realize what parameters that you can feed into those filters. Then on top of these few of areas, we also have inherent nature of the cell. Okay, here is an example of one cell that we have captured. The cell's capacity do change over the number of cycles. So when you say example like this, you have a water bottle, you take the water like exactly 1 liter, you pour it out, then you fill it back in, you pour it out, you fill it back in, you pour it out and then fill it back in. So during this process, imagine you lose a small amount of the water, right? Imagine it may stick to the surface of the the storing unit, or it may get evaporated, um, anything of that sort, right? So the same way in the battery, because of charging and discharging and charging and discharging, we lose some amount of ions. They may get stuck, they won't come back, maybe can be called as lithium plating, or they may be lost in the process of SEI layer formation during the operation of the cycle. There can be situations like that you lose ions. Basically, the ions are the one that stores the charge, right? You lose them. And then when you lose them, let's say the cell which was called as 10Ah or a 5Ah is no more a 5Ah or a 10Ah cell. It is maybe at about a 4.5Ah. That means it has lost about a zero point 0.5 amp hours capacity. That means it might have lost that much amount of ions somewhere in the cell, right? So because not all the reactions are irreversible, though the charging and discharging is, but not 100%, right? Every time when you do that, you may lose some amount of ions in the charging and discharging process. So how do you know if I charge this many number of times, I lose this much, correct? And the aging depends upon many things, right? It's not just charging and discharging. It depends upon the temperature at which you're charging and discharging. It depends upon the SOC at which you're charging and discharging, right? Not every time you do go to 0, 100, 100 to 0, 0 to 100. You may like charge it between 20 and 80, 30 and 70. Every day you have your own pattern, right? That the way you use your vehicle, you use your battery. Uh, what SOC at which you store your battery, right? Because it also has function of calendar gauging, correct? Though you don't use the cell because you just kept it idle, it also builds up certain amount of internal resistance gradually and slowly, called calendar caging. So how do you account in your algorithm? Because in your um, Coulomb counting, right? So we feed a value of nominal capacity, right? So how is that nominal capacity always the same? No, it is not the same, right? It is a function of many things. Capacity itself is a function of many things, and one of the function is aging, right? The aging factors need to be considered, and that is important as a part of it. Uh, so how do you parameterize that aging characteristics into one table and then fill in that, okay, this may be an expected capacity that you can get. Similar way, we have noises. That is also because of the voltage sensor, not just the current sensor, because of the voltage sensor as well. Imagine you're measuring an OCV of the cell. You see a small like fall up and down of the voltage. So which do you consider as the right voltage when there is a up and down going? This is a realistic measurement of the voltage sensor data out of the AFE that you're trying to use. You would see these variations, right? And these fluctuations can create a small offset of your SOC, and that offset can do something else when it is in operation in place. So this is also another challenge that you face as a sensor noise that impacts the measurement of an SOC. Um, what are the things we would use? Let's say initialization at startup. Um, how where exactly that voltage noise can create a mess is that, let's say, when you take a BMS, when you take a pack, imagine an X guy has made a pack and you are giving a BMS, right? uh, you put a BMS into the pack, and how does the BMS understands itself what is the state of charge of the battery, right? You cannot put that as a value and hard write it to every BMS you sell it, right? And it is measuring the open circuit voltage of the pack and then trying to say, okay, hey, this is my SOC. And if you have those noises, which is like this, it would be slightly incorrect that it is setting its first point. Let's say you have the watch. Um, imagine the needle for the second value is offsetted by about 2 seconds, right? That means your minute and then hour needles are at exact 12, but your second needle is slightly by offset. If you start at that point, then your clock definitely would have error, right? So the same thing here also. That when you start your BMS at the very first of its life, so it takes the OCV as a reference to take the SOC, and then you do charging, you do discharging, you do Coulomb counting and all of that. But that point is very important, okay? And what you're setting as a value. And also you take the data as a point at any time. If you see any error in SOC, there is a drift in SOC. So you take a OCV as a measurement and you reset your BMS to go back to that state. And when you have an incorrect OCV, it suddenly sets the incorrect SOC as an update in the resetting. And that becomes an important factor, that why and how important it is to measure the OCV of the BMS, OCV of the battery, and also consider the voltage noises in the measurement. Um, you have other situations like pack configurations. You have situations of inconsistent discharge across the pack that we discussed in the very first slide, where we say if there is incorrect IR across the pack, there could be a significant discharge in some cells, and some cells may be not discharging completely as the cells which are closest to the load. Some of them will create imbalances. So at a primary scale, it is very important that you take consideration of imbalance. So imbalance need to be lowest. That is one of the most important thing. If the imbalance is inherently there inside the pack, the BMS cannot do anything. And we started this journey in the beginning of our projects as well, that the pack manufacturer would say BMS is not doing its job and it is not measuring SOC correctly. Uh, but when we tested it, that when you say OCV stage, everything is okay. But when you discharge the pack, you see the voltage of the cells like not on the same line, they're getting dispersed. And because of that, maybe one cell will hit another voltage and then the cutoff will happen. And the BMS need to show if one cell has hit another voltage as a 0% SOC, so that the BMS doesn't allow any further discharging to happen as a part of the process to protect the cell from not going to another voltage, right? So that's the way. Fundamentally, the battery has to be at a very ideal electrical conditions and have a least voltage differences during its operation and being fully well balanced. Yeah, that's the quick idea. And we have impacts of temperature because temperature also changes the capacity of the pack. Because if you take a cell, test it at 5 different temperatures, it would not give you the same capacity. So how do you account those factors into a place to measure and true SOC? Then you have certain computational challenges, like you can use, people talk about machine learning and all of that, but the problem is, does your hardware practically, like a microcontroller can do a lot of those computations, and these computations will also create a lag, and then how effectively are you able to do this activities within the hardware? So all of these things would lead you into challenges of the SOC estimation, which you may come across on a day-to-day basis. What errors does BMS are able to throw up? That's the quick idea. I wanted to bring it to you through the course. If any questions that you guys have, would be mostly welcome to put them across, and I would be able to answer them. Um, okay. What about the certificate SOC from Decibels? What about the certificate SOC from? Okay, the team will send you a link by the end of this webinar. Filtering voltage measurements can nullify this negative impact, right? You can do, but I mean, it may be very straightforward that we say, okay, hey, we put certain capacitors and resistors and maybe a physical level filtering, but still there will be some amount of uh, measurement inaccuracies that will be there that would still create some errors. With all the possibility of filters and everything, there are measurement errors because you have a certain level of ADC errors and things like that, which would come out end of the day, still if you put everything into the picture. Please emphasize why ML is needed. Okay, so consider now it's like a nonlinear system, right? So you have come across something like an um, linear control system and a nonlinear control system, right? So it is not very straight uh, to 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 say put one table and say, hey, this is the way the battery will degrade, right? You cannot define like a table and say, hey, my battery charging and discharging, and then the battery degrades like this. It is not linear in nature, right? It is non-linear. So you cannot put anything as an equation and define this is the way it behaves. So when it doesn't behave in that way, you cannot constrain that whole behavior in the equation. You cannot picturize it through set of formulas. So that is why, at a very simplistically, if I can tell you, we need a machine learning, right? So you have a data, you let that data decide how the battery behaves. Okay. You have large set of data. Let's say you have thousands of vehicles running on the road. You collected all the data, and then now you have your data which is running on your vehicle. You can compare that data, feed the data to a machine learning algorithm, and that takes sampling across your previous data points and then try to estimate. It is maybe better. I have not tried it on my hardware, but the reason why we do it is because you cannot factorize any of your nonlinear behavior as an equation. So you need something which is broadly variable and take a samples of it and try to compare. So that would be possible why you need a machine learning and AI to do things like that. Software filtering by moving average would be possible. Can we also estimate remaining user life, useful life? Uh, it is possible. That is basically a state of health algorithm, right, which does that kind of an estimation. There are very rudimentary approaches. Do a capacity counting, know how much capacity you captured through the charging and discharging process. Use that as a reference to estimate. You can do IR estimation, check if the internal resistance of the pack is at certain level, and then compare that to a given acceptable limit by the cell manufacturer. You may do some comparisons of that sort. Or there may be again ML and AI based algorithms. People talk about it in the internet, and you have papers available also possible to do that way of estimation. Um, okay, right. Um, we aside of aging, the battery pack actually have experience expiring date. Aside the aging of the battery, do they actually have expiry date? Can temperature from holding iron cause it too? Um, okay, I have not come across expiry date of the cell. I have not seen them printed on the cells. Uh, Obviously, any material will have. There is no doubt about it. It should have, if practical to tell you, but it depends upon how do you use them. Okay. Imagine you charge the battery, you keep it for 25 years. Okay. Maybe it would behave differently. But if you take the battery, charge it, discharge it, maintain it at specific SOC level, it may not degrade as same as the cell which is kept at X temperature, X SOC without using it. Okay. Uh, it should have an expiry date. There is no doubt about it but it may not be constant as a value you can define based on how do you use them. What is the major drawback according to you? PINN, maybe are you talking about something like a single particle model? If it has SPM, just maybe give me a clarification on that. How is it different like SOC, SOH? Okay, I think you can definitely. SOC is state of charge, as I discussed, amount of available charge at any given time. DOD is inverse of that. Let's say SOC is 80%, DOD is 20%. It is 1 minus SOC. Okay. SOH is state of health, which is basically telling you, imagine a person, how healthy is he? Okay. It's a relative term, right? Can he run 10 kilometers? Yes, he was able to run, but today he's not able to run 10 kilometers. Maybe he's not as healthy as the guy who was running, the same guy who was running 10 kilometers, right? So it is maybe something not fit in himself to run 10 kilometers. Maybe he's running 8 kilometers, right? The same way the SOH is ability of the cell to deliver the output capacity, also output power. Cool. Yep. I haven't explored much on that neural network models right now, um, but something we have done in the physics-based models, but I do not have a comparison. I can tell you how different both of them in comparison today. Ujjwal, if we want to specialize in, okay, I would say start practically building algorithms, implement them, have maybe start at a pack level, small pack, NMC, LFP, and then start implementing them and take one step at a time. You would build the experience by failing at every step, and that would give you a better learning experience in an overall way. Um, I think there is no tool today people can just provide you and to say it is a right way or wrong way, but you can approach by starting yourself with a simple small pack and then explore yourself to a variety of chemistries. Should be a good way. Yep. We have maybe if you're interested, we have courses available at Decibels Lab. If it interests you, you can take a look through that. There are modules that we teach on how to do the complete algorithm development. Excellent. So I think we tried to touch base all the questions, and I hope I did my job well today in sharing whatever I know. Um, I know as a webinar, it's like a 5 years of exposure that we might have would be able to share something that I could come across in 45 minutes. I believe it was productive. I believe it was useful for for everyone who have participated. So okay, uh, maybe if any questions left over, we overfilled the duration of the session. I would take them. Maybe you can write me an email. So my email ID is this. Yeah. My email ID is this. I've typed in the chat box. You can drop me an email. I try to get back to you on the questions. Great. So excellent. So thank you very much, everyone, for participating. Thanks a lot, showing your interest and being part of the sessions on the late evenings. Looking forward to see you in the upcoming webinars. Thank you very much, and good night to all of you.